After completing the depression of freezing point of solutions, now I come to explain the osmotic pressure of solutions, which is the fourth colligative property of dilute solutions, and it is under the chapter of the applications of thermodynamics in two-phase equilibrium. Acknowledged in 1746 discovered one phenomena, and this phenomena is called osmosis. And what is meant by osmosis? Whenever a solvent is separated from this solution by means of a semi-permeable membrane, or solvent will move from solvent side to the solution side through this spontaneously through this semi-permeable membrane, and this semi-permeable membrane allows the solvent to pass through but restricts the movement of this solute, maybe due to its bigger size. And if I give a very simple sketch of this process of osmosis, this is a very important scientific phenomena, and the sketch should be like that. A simple U tube. Here in the middle of this U tube, we have placed the semi-permeable membrane, and in the left hand side we have taken this solvent. We have taken this solvent, and the right hand side it is the solution, and solvent and solutions are separated by this semi-permeable membrane. And here it is the piston on the solvent side, and the pressure exerted on this piston is P0. Here also the piston in this on this piston, this pressure is exerted P0. P0 may be taken as 1 atmosphere, means that these two solvent and solutions are placed in 1 atmosphere pressure. And you know the process. Whenever the solvent is separated from the solution by semi-permeable membrane, the solvent will move from the solvent side to the solution side spontaneously with its own accord, and the temperature may be taken as the T, which may also be taken this room temperature. So under this condition, both these pistons are under this same pressure P0 and the same temperature T. The solvent moves spontaneously, and this is called osmosis. Whenever the osmosis starts, the level of this solvent falls, while the levels of this solution will rise, and there develops an hydrostatic pressure on the side of these solutions, and this hydrostatic pressure, when increasing, the flow of the solvent becomes slowed down. At a certain hydrostatic pressure developed on this solution side, this flow of this solvent is totally checked off, means osmosis stops. That hydrostatic pressure so developed on this solution side we call the osmotic pressure. But the osmotic pressure we can define in some alternative way. So suppose this is the original levels of this solvent and solutions on this both sides of this semi-permeable membrane. Now if we add some excess pressure on the piston of the solution side, means simply we are putting this weight, putting the weights on this piston, and the pressure is developed on this solution side, excess pressure. And whenever the excess pressure becomes such that the solvent will not at all move and the level remains fixed at this position, and that pressure, suppose that pressure is pi. Pi is the excess pressure or additional pressure applied on the solution side in order to check the osmosis, and this pi is called the osmotic pressure of this solution. And this osmotic pressure is also a colligative property which depends on the number of solute particles relative to the total number of particles in this solution, and does not depend on the nature of these particles like size, charge and mass of this particle does not affect the value of this osmotic pressure. It only depends on the number of solute particles present in the solutions in a given amount of this solvent. And the origin, if we seek, if we consider, if we try to search for the origin of development of osmosis, then we have to go again the very fundamental property of thermodynamics, which is the chemical potential of this solvent. And origin or cause, origin of osmosis, we can easily explain in terms of the chemical potential. And suppose this excess pressure is not added and the solvent flowing, osmosis starts. Why the osmosis occurs? That is being explained by the formula, this mu1T and P0. It is the chemical potential of the solvent at temperature T and pressure P0 is equal to the chemical potential of this pure solvent at the same temperature and P0 plus RT and ln x1. x1 is the mole fraction of this solvent in solution. These equations I have written several times in my previous lectures. This is the chemical potential of the solvent in solution. This is the chemical potential of this pure solvent, and x1 under the same temperature pressure, and x1 is the mole fraction of the solvent in solution. So this in x1 x1 is always less than 1 in solution. So actually ln x1 is less than 0. So this one is a negative. These two are positive, this is negative, so this one is greater. It means mu1 naught T and P naught is greater than mu at a temperature T and pressure P naught. Means chemical potential of this pure solvent is greater than the chemical potential of this solvent in solution. This solution is made up of non-volatile, and here we consider this non-electrolyte solutes, and whenever the solute is added, the chemical potential of this solvent is lower down. So this unbalanced here it is mu1 naught and T and P naught is greater than mu1 T and P naught, and this unbalanced chemical potential becomes a driving force for the flow of this solvent from this solvent side to the solution side. As we know, chemical potential is a measure of escaping tendency of this substance, and it moves spontaneously from the high value of chemical potential to the lower chemical potential, to the site where chemical potential is lower. Now it is a question when this process will attain equilibrium. This is now coming a very important question in our study. If we place the excess pressure, additional pressure, which is equal to the osmotic pressure, then this one stops. Means the system, the levels remains in its original position. Means in that case, the solvent in pure state and solvent in solution both are at equilibrium, and the condition for this equilibrium is that this mu1 naught T P naught is equal to mu1 here T and pressure P naught plus pi. Means excess pressure which is added on the solution side, this excess pressure will increase this chemical potential of the solvent in solution. So this equilibrium is being attained and no flow of solvent occurs. So this is the origin. Lowering of chemical potential of the solvent in solution is the cause for the development of osmosis, and this pi is the osmotic pressure. Now we come again another very important process here. It is suppose P is greater than P naught. The excess, the P minus P naught is the excess pressure on the solution side. Depending on the value of P, there are three different cases that may arise. Say case number 1. When P minus P naught is less than pi is the osmotic pressure of this solution. And in this case, the osmosis still occurs. Osmosis still occurs. And case number 2, when P minus P naught is equal to pi, means osmotic pressure, the excess pressure on the solution side becomes equal to the osmotic pressure, the osmosis stops. Osmosis stops. And the third case, very interesting. When the pressure, when P minus P naught is greater than pi, means whenever the excess pressure on the solution side is given greater than the osmotic pressure, then the chemical potential on the solution side, chemical potential of the solvent on the solution side becomes greater than the chemical potential of this pure solvent at this temperature T and P naught. Since this excess pressure is greater than osmotic pressure, so here the chemical potential of the solvent in solution is also increased. Then this one, we know actually this del mu by del P at constant temperature is equal to V bar, and this V bar, molar volume, is always a positive. It means that whenever the pressure is increased, the chemical potential is also increased. Whenever the pressure on the solution side is kept greater than the osmotic pressure, the chemical potential of this side is higher than this value, and the solvent will move from solution side to this solvent side. And this phenomena is of very interesting to us, and this phenomena is called, means a solvent. In that case, solvent moves from solution side to the solvent side. And this phenomena has given the name back osmosis. Back osmosis. This is given the name as a back osmosis, or called very popularly reverse osmosis. Reverse osmosis, very popularly known as RO. You can find this term RO in several products also. In case of in this case of, say, common salt packet, it is written as RO. Means the salt is extracted from this seawater by means of this reverse osmosis. And whenever the solution is much more seawater, concentration of seawater with respect to the sodium chloride is much increased. It is laid down over the long trays under the sun, and it is called sun dry. And in every salt packet you can see the sun dry and osmosis, these two terms are given. And reverse osmosis, RO, not only here but also you find applications in other fields. Suppose suppose some persons moving in a ship on this ocean, and this drinking water in this sea is totally exhausted. Now it is a question how to get this drinking water in this ocean. Ocean water, or you can say ocean water, is saline and not fit for drinking. This Milton's that very important poem, water, water everywhere, but not a drop fit for drinking. So what you can do in that case, you can utilize this reverse osmosis. Reverse osmosis would be used. Suppose this is the sea and or the ocean, and here you just place one tube, and the bottom of this tube is packed with this semi-permeable membrane, which can allow the water to pass through, but these salt particles it will not allow to pass. And so actually the osmotic pressure of ocean water or sea water is equal to 27 atmosphere. So this tube is lifted to the bottom, so that this pressure has been created. And whenever the pressure is created over this one, this solvent, pure solvent from this sea water will enter through the central membrane to this to inside of this tube, and this pure water is being pure water is collected within this tube, and when sufficient water have been collected, it could be taken up by means of suction pump. So you can easily get this pure water from this sea water. This similar process you can see in costly water purifier. The two terms have been noted there. One is UV and other is RO. UV actually kills this germs in this water, raw water, and RO filters to get this pure water. So UV and RO, these two terms now widely used in costly water purifier for drinking purposes. Now actually it is not necessary to keep this solvent here. If the two solutions may also be placed on the two sides, and here the lower concentration solutions, here the higher concentration solutions. In that case also the osmosis will also occurs, and solvent will move from this lower concentration solution to the higher concentration solution until the chemical potential of the solvent in both the cases becomes equal. Actually, you see interesting information also here is that the blood red particles or red corpuscles, the red corpuscles, this is the blood red corpuscle, or you can say this red cell, blood red cell in blood. This one is isotonic. Whenever the two solutions having the same osmotic pressure, we call the isotonic solutions. Whenever the two solutions having the same osmotic pressure, we call these two solutions are isotonic. Here, the blood red cell is isotonic with 0.85% sodium chloride solution, aqueous solutions. So this solution is called the normal saline, and this solution is injected intravenously in a patient when the patient is suffering from dehydration. And this solution is isotonic with this blood cell. So the size of this blood cell remains intact. But whenever this solution is sodium chloride solution is taken this lower concentration of this one, then it is called hypotonic solutions. When the concentration of this sodium chloride solution becomes less than this one, it is called hypotonic. And if these red cells have been kept in hypotonic solution, the water from hypotonic solution, water from sodium chloride, hypotonic sodium chloride solutions will enter into the blood cell, and blood cell is swelled up, and may also happen that it bursts out. And on the other hand, if we take this concentration of sodium chloride greater than this one, this is called hypertonic solutions. Whenever this blood cell is within the hypertonic sodium chloride solutions, the water is coming from this portion to outside, to this solution, to the hypertonic solution, and this blood cell will be squeezed. In both the cases, if we use this hypotonic or hypertonic, in both the cases, some physiological disorder may happen with the patient, and so the normal saline is used to inject intravenously to prevent the hydration of this patient. Another example I can also put here. Suppose the dry grapes, which we call in Bengali kismis. Suppose here the one beaker or any container which you have in your household, and taken this water is taken, and if you place one resin, means dried grape, one dried grape which is in this way, the shape is like that. But whenever you keep this raisin or kismis in water over the night, you will see this water enters into this kismis through this cell, and these cells are acting as semi-permeable membrane, and this kismis becomes swelled. But means again, if you this swelled raisin is, if you keep here in concentrated sodium chloride solution or concentrated sugar solution, then again it comes back to this squeeze state, means water is coming out from this raisin and it is also squeezed and forms this original shape. These are all examples of this osmosis or hypotonic, isotonic, hypotonic and hypertonic examples. Now we like to talk about this semi-permeable membrane. You know, there are so many natural semi-permeables are there. The egg shell lining, parchment paper, cellophane papers, and the vegetable skins, they are all natural semi-permeable membrane, and they are useful for these natural processes to occur. Several natural processes are occurring, and this semi-permeable membrane are used. But whenever we are using this reverse osmosis process, the high pressure is required to put on the solution side, and in that case the semi-permeable membrane must have to withstand such a high pressure, and so we require the preparation of artificial semi-permeable membrane which can withstand very high pressure, which is required for this process of reverse osmosis. And this preparation of artificial SPM, very easily we can prepare this artificial semi-permeable membrane. Suppose very simple method I can show here. This is U-tube, two limbs are here, and in the middle of these limbs we place some porous wall, and these are the pore channels. These are the pore channels, such as the burnt clay block or porcelain block. They have several pore channels within this block. Here you can take this copper sulfate solution, aqueous solutions, and here aqueous solutions of potassium ferrocyanide. Solution, all are aqueous solutions. Both the two are dissolved in water, and they are taken on both sides of this porous wall. And actually one substance which is copper ferrocyanide. Copper ferrocyanide, a brown color material. Whenever this copper ferrocyanide is deposited on these porous channels, and whenever it totally blocks these porous channels, this block acts as the semi-permeable membrane that can withstand very high pressure. So, in order to, copper will go this side, ferrocyanide comes this side, and they will meet on this. Whenever they will meet on these pore channels, they will form this sort of precipitate. But to accelerate the process, here some driving force. Here one platinum plate. Here is another platinum plate have been dipped, and these two are connected with a battery, and here is one electric bell. This is the electric field is inserted to accelerate the process of ongoing migration of copper ion and ferrocyanide ion. Copper 2 plus will move from left to right. This is the negative electrode, means the cathode, and this is the positive electrode, and this is the anode. So cation, copper ion cation will move towards this cathode through this porous barrier, or pore channels. Similarly here, the ferrocyanide ion, which is anion, ferrocyanide ion will also come from right to left through these pore channels. Whenever these two ions meet together within these pore channels, they will form this precipitate and block and will block these pore channels increasingly. The bell will ring so long the ion can move through these pore channels, means current is flowing. But whenever these pore channels are totally blocked by this precipitate, the ions cannot pass through these pore channels, and in that case the bell will stop ringing. And so this one, whenever it is blocked totally with this precipitate, this one acts as a semi-permeable membrane, artificial semi-permeable membrane that can withstand very high pressure. Now I like to propose one equation which is called the Van 't Hoff equation. Van 't Hoff equation in the 19th century. Van 't Hoff awarded Nobel Prize, Dutch chemist, extensively investigated the osmotic pressure of solutions having different concentrations and at different temperatures. And he collected so many data, and by the use of this experimental data, he formulated one empirical equation. This Van 't Hoff, which is known as Van 't Hoff equation of osmotic pressure. He found that osmotic pressure of a solution is proportional to C, molar concentration of the solutions. Here there occurs no change in temperature, so this molar mode of concentration may be used. to represent the concentration of the solutions. When T is kept fixed, it is quite natural whenever the concentration of the solution is increased, the osmotic pressure of the solutions will also increase. And case number 2, phi is proportional to T when concentration is kept fixed. With the rise in temperature, the osmotic pressure is also increased. And this could be done by doing this experiment in a thermostat of a varying temperature. So whenever these two equations are joined, then it becomes phi proportional to Ct. And whenever it becomes equal, some proportionality constant, K is the proportionality constant, is inserted to make it equal. Pi is the osmotic pressure of the solutions having the concentration, molar concentration C at this temperature T. K is the proportionality constant. And you see, I shall also illustrate in my next class how the osmotic pressure of a solution could be determined by a Berkeley-Hartley methods, and so many other methods are also there. Osmometer nowadays are very popular, very sophisticated instrument to determine osmotic pressure very accurately of the solutions. So whenever this concentration and temperature and phi all are known in this equation, then it is found that K, the proportionality constant, becomes equal to R. R is the universal gas constant. Actually, unit and magnitude of K is identical with this value of R. So instead of writing this K, we can write the event of equation phi equal to CRT. This is equation number 1. If you know the concentration and temperature, then you can calculate the osmotic pressure of the solutions. So though this expression or this equation is valid for ideal solutions, so it is valid for ideally diluted solutions, and the solute is non-electrolyte and non-volatile. These are the restrictions. And the other forms of this equation, we can write this C, molar concentration, equal to number of moles of the solute dissolved in V liters of the solutions, into number of moles of the solute dissolved in V liter of the solutions. So replacing this C and making some arrangement, we can write a pi V equal to N2 RT. This is equation number 2. Here pi is the osmotic pressure, V the volume of the solution which contains the N2 moles of the solute. Solute must be here non-electrolyte, R the gas constant, T the temperature. You can see there is a surprising strike or remarkable striking similarity between this equation and this pressure of volume equal to nRT, ideal gas equation. This is ideal gas equation. And this is valid for ideal solution. So you can see both these two are having striking similarity. This is the ideal gas equation and this is the event of osmotic pressure equation. And seeing this amazing similarity, Van Hoff himself remarked, as the osmotic pressure of a substance in solution is equal to the pressure it will exert if it were in gaseous state, occupying the same volume of the solution at the same temperature. And this is the Van Hoff's remark by seeing this striking similarity between the two equations. But actually, though these two equations are similar in external features or say external form, but there is a basic difference from the origin, from the origin point of view. Here the N is the number of moles of these gas molecules which are striking the walls of the container, and this pressure P is developed. So here in the case of gas, the pressure is originated due to the collision of the gas molecules on the wall of the container. But in this case, the osmotic pressure is developed due to the unbalanced chemical potential of the solvent and solution, so when they are separated by a semi-permeable membrane. So origin is totally different, but surprisingly they are having the striking similarity in their external forms. And I can show another very important similarity. Suppose here one cylinder is taken, cylinder is placed horizontally fitted with a piston, and piston is movable horizontally, and piston is a semi-permeable membrane. This wall is a semi-permeable wall, means it will allow the solvent to pass but restricts the movement of this solute from the solutions. Here you can write this solution and here the solvent. And you know the solvent is a pure solvent. Solvent is having the high chemical potential, then the solvent in solutions. So this unbalanced chemical potential drives the solvent to the solution side. As the solvent is coming to the left, the piston is moving to this right, and as the solvent is moving and flowing or passing through the semi-permeable membrane, the piston is shifting to the right hand side and first and comes in contact with this wall of this container. So this may have some similarity with this gas. Suppose if we take this gas here and it is the empty space, vacuum, then gas molecules will strike this wall and push this wall towards this right, and this movement of this piston occurs due to the striking or collisions of these gas molecules on the wall of this piston. But in this case, it is not that the solute of these solutions are striking this semi-permeable membrane wall to push aside. This process is coming due to the unbalanced chemical potential of both sides of this semi-permeable membrane. So though the similarity is there, gas is passing through this gas is expanding just like the free expansion of this gas against the vacuum. Though similarity is there, but basically, originally, these two processes are different. Now I give one problem. Suppose N2, number of moles of this solute is weight of this solute and divided by molar mass of this solute. If we replace this N2 by this way, then actually and rearranging, we can get this pi equal to W2 by M2 and here RT divided by V. This is equation number 3. So if we know the molecular weight or molar mass of this solute must be non-electrolyte in this case, then osmotic pressure of this solution could be determined. V, the volume of this solution which contains W2 mole, W2 gram of this solute at the temperature. And I can get one simple problem. This equation is widely used to determine the molar mass of this solute. And since this property does not depend on the nature of the solute particles, does not depend on this mass, does not depend on the mass, size, charge. So this equation is equally applicable to determine the molar mass or number average molar mass of this polymers. And this one I shall discuss in my next class. Now one simple, very simple problem. Calculate osmotic pressure of 3% aqueous urea solution at 27 degrees centigrade. Very simple. 3% means 3 grams of this urea is dissolved in 100 ml or 0.1 liter of these solutions. If we do this problem, solve this problem, then pi equal to, here W2 is 3 gram and the molar mass of urea is having this formula CONH2 and whole 2. This is the formula of urea. If we calculate the molar mass, then it will be 60 gram mole inverse. Now R is 0.082 liter atmosphere mole inverse Kelvin inverse, and the temperatures 27 degrees centigrade to be added with 273 and it becomes the 300 Kelvin and divided by the volume is in liter, so 0.1 liter. If we cancel this like units, Kelvin inverse Kelvin, mole inverse, gram, then calculations will give the 3 into 0.082 into 300 divided by 60 into 0.1 atmosphere. If we do the calculations, then 12.3 atmosphere is the osmotic pressure found for 3% aqueous urea solutions at 27 degrees centigrade. This is all about the explicit discussions of this osmotic pressure of these solutions, and in my next class I shall discuss the experimental determination of osmotic pressure so that the molar mass of the solute could be calculated, and the thermodynamical derivation of the Van 't Hoff equation also I shall explain. And next, the four colligative property are connected, so that if you know the one colligative property of a solution, then other colligative property of the solution could be calculated by this interrelated formula. So thank you all who are watching this video. If you like, then please subscribe. Thanks.